Okay, hey everyone. So we're going to get started looking at the central limit theorem. Now, uh, it'll take me a while to tell you what that means, but one of our objectives here are by the end, you're going to be able to state what the central limit theorem says, and we're going to be able to do something with the central limit theorem that will help us understand sample means. So we're going to be able to find the probability that a sample mean x bar falls within any specific interval. And now it's also going to apply to the central limit theorem will also help us with other sample statistics, like p hat, for example. Now, before you watch this video, you should probably make sure that you've really understood the previous section, 6.3, which is about the sampling distributions. These are very closely related topics, so you'll probably get a lot more out of this if you are really solid on the previous topic. Okay, so let's get into it. Now, the central limit theorem, it's a fundamental fact that comes out of probability theory, and essentially the reason we're interested in it is that it's going to give us very useful information about the sampling distributions of x bar and other sample statistics. Okay, so it's going to take us a while to build up to that. So to build up to that, we're going to first have to look at what happens when you add together random variables. Okay, so let's look at an example of that. Okay, so this is a couple of distributions that we've already seen in some of the earlier tutorials, right? The height of women in the world and then the height of men living today in the world, right? So this is data that was collected by this resource, Our World in Data. Okay, suppose you select a random man and a random woman. Let the man's height be x and the woman's height is called y. So we know that the distribution for y is this blue one here, and the distribution for x would be this red curve. Okay, so those are both normal distributions, right? You can see the shape, they have the typical bell shape. Now, if you read these figures carefully, you can pull out that the fact that the distribution of x, so the men's heights, it's a normal distribution with the mean, the population mean, being 178.4 centimeters. So where's that coming from? It's just the center. It's also the median, right? But it's the mean for our purposes. And the standard deviation for the men's heights is 7.6 centimeters. So where does standard deviation appear? It's this height, it's this width, right, between from the middle to the steepest point here, 7.6 centimeters. Okay, and then the same parameters for women is the mean is 164.7 and the standard deviation is 7.1. So let's see. So for women, sigma is here. And notice I'm using subscripts. So the subscript means just the letter is written kind of a little bit smaller and down. And the subscript tells us which variable are we talking about. It's the sigma for x for men, or it's the sigma for y for women. Oops, it's 7.1, right? And so we're going to be using the subscripts constantly from now on because we'll have more than one random variable we're dealing with. We need to keep track of which one's which. Okay, so we're going to combine these two together. So imagine now that you select a random man and a random woman. And then we're going to take the two heights and we're going to add them together. Okay, so we're going to add together the x value and the y value, and we want to know what is the distribution of the sum x plus y. So you could think of it like maybe we're looking at all the married couples in the world or something like that, and we're saying, well, if we know how the men's heights are distributed and the women, what about the sum for all the couples out there? Okay, so what is the we know that when we add them together, the average is going to be bigger, right? And in particular, the mean of the sum is going to be just the average man plus the average woman. So how we would write that is the mean, mu, for x plus y. So we're going to write x plus y as the subscript. The mean for x plus y is going to be, so the mean for men, which is mu x, plus the mean for women. So we just need to add the two averages. And that should make some intuitive sense to you, right? The average weight of a couple is going to be the weight of an average man plus the weight of an average woman. I doubt that you really feel need for more explanation of that, right? Now, but it's going to be trickier as soon as we say the variance. So what about the variance of x plus y? Let's think about that. So what I'm asking is, what would be the sigma squared for x plus y? What's the connection between how spread out are the men, how spread out are the women, and then how does that relate to how spread out will the couples, the sum of those two be? And when I think about it, the weights of a couple, so two people, it's going to be more spread out than the weight of any individual person. Why is that? Because you have two people to work with. They might both be very, I keep saying weight, but it's height, right? They might both be very tall, in which case, or they might both be very short. So since those are possibilities, the distribution is going to be wider, right? So there should be more variance in the sum. And fortunately, the actual relation is pretty simple. So the variance of the sum is just, again, it's the sum of the variance for men plus the variance for women. So notice that means that the variance for the couple is larger than each one. The variance for a couple is definitely larger because it's the sum. Than the variance for either a single man or a single woman. I don't mean single as in marital status. I mean just an individual, for an individual man or woman. And why is it that you just need to add up the two variances? Well, we could prove that, but we'd have to go deeper down into the details of the theory for random variables. We're not going to do that right at this moment. Okay, finally, the shape of this distribution is going to be normal. The distribution for, as in the distribution for x plus y is going to be normal, and that's because both x and y are normal. So whenever you add together two normal variables, you can be sure that the result is still a normal variable because both x and y are normal. So we can summarize this with a little picture here. So let's say this axis is the height total x plus y. I need a little bit more space, so let's put it here, x plus y. Then the distribution of x plus y is going to be normal, with the mean here is mu x plus mu y, which is Oh, we didn't even calculate it. We should have calculated it up here. So what is the mean for men? It was 178.4, and women was 164.7. So what's the total? (343.1). So the average couple height will be 343.1 centimeters. So let me put that number right there, 343.1. And what about the variance? You know what? I need this space here, so I'm going to delete this little comment. I think you heard it, so hopefully that will stick, because then I can actually calculate it here. So what is the variance for men? It was 7.6 squared, right? Because I know sigma was 7.6. So the variance is 7.6 squared. And then for women, it's 7.1 squared. So what do I get? 7.6 squared plus 7.1 squared. 108.17. Now, now you're probably thinking, well, how wide is this curve? Certainly not 108.17, right? So what's the standard deviation for the sum? What we need to do is we need to take the square root of that number. So the sigma is going to be square root of 108.17. So the square root of that is 10.40. 10.40 centimeters. So notice that it's not that we add the two standard deviations, right? What were the two? Notice that if I just added sigma x plus sigma y, what would I get? It was 7.6 plus 7.1. That gives me 14.7. If I just added the two sigmas together, I don't get the same thing here. The standard deviation here is less than just adding the two sigmas together. It's very important that what is added is the variance. This is probably the reason why we even define variance at all, because when you add two variables, the variances add to get the new variance. But then we have to take the square root of that, right? We have to take the square root of that to get the sigma. Okay, so you can see that the couples are more spread out. Couples total height is more spread out, has more spread than individual men or women. Okay, great. Now, if you absorb that, then you've already gone a long way towards understanding the central limit theorem. Okay, now we're going to take the next step. So suppose you select 4 women. Forget the men. Select 4 women. And we're going to denote their heights by y1, y2, y3, and y4. And remember, these are random. These are all random variables. So now we have 4 random variables. And let's imagine if we add up all 4 of those women's heights. What is the distribution of the total height? We'll call it T for total. We're going to add up all 4 of those women. So if we use the ideas that we just went through, the mean for the total, what do you think it's going to be? What's the average total for 4 women? Shouldn't it just be 4 times the average? It is. It's going to be the average of y1 plus, I keep saying average, but I shouldn't. I should say mean. Doesn't matter, though, does it? The mean of y1 plus the mean of y2 plus the mean of y3 plus the mean of y4 and which is all the same. They're all the same number, right? Because these are all the same as y. What was the mean of y? It was 164.7. So I could do that with multiplication, right? 4 times 164.7, which is 658.8 centimeters. Okay, so that's the mean total for 4 women. And I'm sure that that makes quite a lot of sense to you. And what about this, the variance? Sigma squared for the total. We just have to stick to what we learned last time. If I add up a bunch of random variables, then I will also add up the variance for all of those variables to get the variance of the total. So it's going to be the variance of sigma of y1 plus the variance of y2 plus the variance of y3 of y4. And these are all the same. These are all the same. They're all 7.1 squared. So let's call that 4 times 7.1 squared, which is what? 201.64. We should put the units in here. So is it centimeters? Actually, no, because the 7.1 was centimeters. So when I squared, it becomes centimeters squared. So then the sigma for the total is going to be the square root of that, 201.64. And then when I do the square root of centimeters squared, I'm going to get back to centimeters, so 14.2. Okay, so what we have just found is that and it's going to be normal. So last point is that t is a normal variable, a normally distributed random variable. Why? Because it comes from adding together random variables. We can always assume that. If you want to know why, we need to study more probability theory. There's always more, right? But we have to draw a line. Okay, so what's the distribution for the total of 4 women? It's going to be a mean of, we just found it, ut was 658.8, and the spread, the sigma, was what, 14.2. So notice, this is really important here. Notice that t is not just 4 times as spread out as y. As one woman, right? The sigma for one woman was 7.1, right? Sigma y was 7.1. But what was sigma t for 4 women? It's 14.2, which is what? You can see that's just double. It's just 2 times sigma y. So we have 4 women, but the spread is only twice as wide. Why would that be? It's because if you take 4 women, it's very unlikely that they're all 4 going to be tall, right? Probably some of them will be shorter than the average. So when we add them together, the shorter ones plus the taller ones will kind of pull each other towards the middle. So if we add up a bunch of, I'll just say it again, when we add up multiple people, it's very unlikely that they're all going to be on the one side above average. And so they're not going to be as spread out as you might expect. You're going to have some kind of, you might call it cancellation or smoothing, averaging. Okay, we're going to get deeper into that, don't worry. Okay, so now suppose again, you randomly select 4 women. We just did this, right? Again, their heights are denoted y1, y2, y3, y4. Now we're getting closer to statistics. What is the distribution of the mean height, the average, which is the sum divided by 4? So notice that y bar, the sample mean, it's the total divided by 4. Now, here we have to think a little more creatively. What is the mean? So then the mean for the mean of the sample means, the mean of all possible sample means is mu y bar. Now let's think about it. We can see right here that y bar is t divided by 4. Excuse me, t divided by 4. So what will the mean of y bar be? If I have a random number and divide it by 4, don't you think that the average of that will be its average divided by 4 also? That's what it is. And well, what do we know about that? What is mu t? We knew that mu t was 4 times mu y, right? It was the mean of the total of all the women was just 4 times the average woman, mu y. And then I have to divide it by 4 there. So what happens is these 4s just cancel out. So what I have at the end is that the mean of the sample means is the mean, right? The mean of the sample means is the mean. Let's write that down. And this, we actually said this in the previous section, in the sampling distribution section. The mean of the sample means is, let's call it the underlying mean. Underlying as in the underlying variable here is y, the height of one woman. So the mean of all the sample means is the height of one woman, the average, the mean height of one woman. Okay, it's easy to get lost in all the words. So maybe that's the reason why we use formulas, so you don't get lost in the words. Okay, and then the last thing was the variance. The variance of all possible sample means is, so it's sigma squared of y bar. Now, this is not quite what you are going to expect here. So here's what it is, and then I'll tell you why. So again, going from this starred equation, going straight from there, what happens is I get it's the variance of t, but then do I divide it by 4? No, I don't divide it by 4. I actually divide it by 4 squared, and which is 16. And the reason for that is let's think about that. So what is the variance of a what is the variance of a variable? Let's just call it sigma squared of x. What's the definition? It's the expectation of x minus the mean squared. And what that means is if I divide x by 4, then what happens? Well, then I also have to divide mu by 4. The mean will also be divided by 4. The mu will be also divided by 4. But what happens to this? But this is squared, but the result is that x minus mu squared is divided by 16. And that's because there's a square here in the definition. In other words, variance is a parabola. Or you could call it, it's a quadratic function. So if I multiply or divide x by a number, the variance is going to be multiplied by that number squared or divided by that number squared. Okay, so that's tricky, right? Now, so let's finish this up here. So that means that sigma squared of y bar is what was the sigma squared of t? It was 4 times sigma squared for just one woman, right? Sigma squared for one woman. I still have to divide by 16. So now what happens here? I can cancel out the 16 and the 4. I just get 4. Okay, stick with it here. We're almost there. What happened? So last step, what is the variance for one woman? It was 7.1 squared divided by 4. Let's see. 12.60. 12.6025, let's say. And so what does that mean about, finally, what about sigma? That's what I'm getting at. What is sigma of y bar? It's going to be the square root of 12.6025. Square root of that. Oops. Square root 12.006. Oops, 60. 3.55. 3.55. And notice, okay, that's less, quite a bit less than sigma y. In fact, it's half of sigma y. In fact, it's half of sigma y. Okay, let me just summarize what we did. The standard deviation for one woman is 7 centimeters, right? 7.1 centimeters. If I take 4 women's heights and find the mean, the average, the spread in the average is now only 3.5 centimeters. So the average is half as spread out. And again, why would that be? Why would the average be less spread out? It's because, essentially, it's very likely that some of the women will be above average and some will be below average. So then when we add them together, the variation in the two directions will cancel out. So we'll have much less variation. Okay, so we're going to summarize this in 2 general facts. So these are, I say facts, but I mean, we could say theorem if we want to be fancy. Theorem is just what mathematicians call a fact when they feel good about it. Okay, so 2 important facts about random variables. If x and y are any 2 random variables, the distribution of the sum is described by this. It has a mean value, mean value of the sum is the mean of the first one plus the mean of the second one. And the variance of the sum is the sum of the variance, which means that the sigma for x plus y, you might look at this and you say, that looks like Pythagoras' theorem, right? It looks like a squared plus b squared equals c squared. And deep down it actually is Pythagoras' theorem. Um, but I'm not going to go deeper into that. So how do I find, like, how do I solve for c if I'm doing Pythagoras theorem? I have to take the square root of the a squared plus b squared. And in fact, this is why if you think of the triangle, the length of the third side, how long is this? How long is the third side? It's not just, you don't just add up these two lengths, right? C is not the same as a plus b. It's less than a plus b, right? C is less than a plus b. And that's the same thing here. The sigma of the sum is always less than the sum of the two sigmas. Okay, that's getting into some deep stuff, but we'll back away from that. Okay, second general fact. If we have multiple copies of the same variable, so if I have x1, x2, x3, up to xn, if they're n separate as in independent instances, think of it like they're all different men. We're picking n different men or n different women. Separate instances of the same random variable x, then the distribution of the mean, sample mean, which is the sum divided by n, it has parameters mu x bar is, well, it's going to be 1 over n times mu of x plus mu of x. And that's, when I write it like that, I mean, because I have n men, so there's going to be n copies like that. But then if I write that in as multiplication, it's n times mu x, but I still have to divide by n. So it's just mu x. So the mean of the sample means is just the underlying mean. And the, oops, different color. The variance for sigma squared, so the variance for x bar is, here's where that tricky part came in. So when I divide by n, it becomes dividing by n squared because it's a parabola. But these are all the addition part is still kind of regular addition like this. Plus, so we're adding all those up. And so how many copies of that? That's n copies, but I'm dividing by n squared. So I get, what happens to the n's here? Here I have one n on top and n squared on the bottom. So so the variance of x bar is the variance of x divided by n. Finally, what does that say about the sigma? Sigma of x, I have to take the square root of that. What's the square root of sigma squared? That's going to be sigma x, but on the bottom, it's the square root of n. So these are three general facts, or sorry, three parts of this second fact that are true for any random variable. That's why this box is important. This is for any random variables x and y, because I mentioned y in the first part. Okay, so we're going to stop this video here. The next thing we're going to do is we're going to look at, under certain circumstances, which are very common circumstances, the distribution of x bar is actually going to be a normal distribution. And that fact is going to be called the central limit theorem. So we'll stop here. See you in the next video.